My name is Roly Perera. I'm going to talk today about a programming language called Fluid with a dependency tracking runtime, and about how this kind of infrastructure might be helpful for creating explorable explanations. So first of all, let me explain what I mean by a dependency tracking runtime. So this is an implementation of a chart in Fluid that shows some non-renewable energy output for USA relative to China. And we use this dependency tracking runtime to implement what we call transparent visualizations. So a transparent visualization is one where, as well as the chart, you also have access to a view of the underlying data. And then you're able to interact with parts of the output, parts of the chart, and see how they relate to the data set. So for example, if I put my mouse here, I can see that these two values, 91 and 61, were combined in some way in order to compute the y-coordinate at this point on the right. And this is impartial information. I can probably guess here that it's a division operation, but that information itself isn't made explicit. All I can see is the data that was being used. But this is what our dependency tracking keeps track of. And we can do this the other way around. I can move my mouse over to the output column, for example, and I can see what output points are consuming the data that my mouse is over. And here, these data elements are coming in pairs because I actually need two data values in order to compute the y element of the point on the right. So in other words, if I'm interested in this value 61, I also need to care about the number 91 because 61 isn't used in isolation by the output. So that's why we see both of these values. So that's the basic idea of transparent visualizations. And let's do something slightly more interesting now. This is how the program is implemented in Fluid, and I don't have time to explain the syntax. I'll just say that it's a pure functional language with a Python-like syntax. So the key point is that the programmer hasn't had to code up any of those interactions I just showed you. They just express their visualization as a pure function of data, and then all those interactions I showed you just came for free. So what we can do now is uncomment this code and have another visualization into the mix. So now we have a bar chart that also shows the same data. And as before, if we move around some of these points, we see the data that was needed. But if we move over the 2015 points, what we'll see is that two of the bars, the China and USA bars in the top figure, are now being highlighted. And if we click on one of these points, we can investigate that. So if we move our mouse over the USA bar, for example, I can see that these four data elements were needed in order to compute the height of that bar. If I move my mouse over the China bar, then I can see that these four elements were needed. And again, it's only partial information. In this case, these four numbers are being added together to compute the height of the bar. I can't see that, I can just see the data dependencies. And I can play this game the other way around. I can, for example, I can click on this bar, and then I can see that these 4 points over here, the 2015 points in the scatter plot, have been highlighted, and I can interact with each of those to see the overlapping data requirements again. And these points don't overlap, which is why they haven't been highlighted. So this is what's called brushing and linking in the data visualization literature, except that here we're doing it in a transparent way. We're able to show how two bits of output are related in some way because they have shared data dependencies. So that's the basics, that's the dependency tracking runtime that Fluid provides. Let's look now at how we might use that to help with the authoring of explorable explanations. So an explorable explanation is a long-form essay that explains some kind of challenging technical idea. So this is an article from distill.pub that explains matrix convolution in a really nice way. I can move my mouse around in the input grid and I can see how data flows through to the output, for example. I can't do it the other way around, but it's still showing me something interesting about what's going on. And there are sliders down here that I can twiddle to get different implementations of convolution. So in Fluid, the way you would implement convolution is like this. Again, it's a pure functional language. So here we've just expressed convolution as a pure function of two input matrices, the image and the filter. But although this code doesn't say anything about interactions, if we load this in Fluid, what we actually get is an interactive version of convolution. And it allows us to move our mouse around on the output, say, or the input, and see the data dependencies. So in this case, as I move my mouse around the interior of the output, I can see that these input elements were needed. And if I move to the boundary, then I can see that parts of the filter now become irrelevant. And that's because the input image is behaving as though it were padded with zeros at the boundary. And if I do things the other way around, I'll see a kind of symmetric usage pattern from the input to the output. And I can see that not every filter element is actually needed for every output element. And I can explore that. So let's go back to the source code for convolution. The way it works is for every output element, we compute a little 3x3 intermediate matrix and then average those elements in order to compute the output element. And this funny bracketing notation is a kind of comprehension notation for matrices that allows us to do that. And we use this auxiliary function called a lookup to return the notional content of the image at a particular coordinate. And the way it currently works is if we're within the bounds of the image, then we just return the actual content of the image at that coordinate. Otherwise, we return 0. And that gives us the zero padding behavior that I just mentioned. So what we can do is uncomment that definition and use this definition instead, which implements wrapping instead of zero padding. If we now look at the behavior of that algorithm, what we'll see is the same sort of behavior as long as we remain within the interior of the image. But when we move to the boundaries, we'll see that the filter no longer becomes partially irrelevant. Instead, what we see is the usage of the input wrapping. And if we go to the input, we'll see a similar kind of symmetric pattern again in terms of how the input elements contribute to the output. And we'll see that every element of the filter is now needed by every element of the output. So this is, of course, by no means a self-explanatory version of convolution, but it's a little bit closer to something that we could use as the basis of an explorable explanation. So let's see if we can go a bit further. So one thing that Fluid allows us to do is attach these decorated dot comments to values. So what I'm going to do here by uncommenting that line of code is attach this dot comment to the intermediate matrix. And if we now interact with an element of the output, we'll see that intermediate matrix pair appear along with the dot comment explaining what's happening. So it's telling us now that it's showing us the 9 elements that were averaged in order to compute the particular output element we're over. And because this dot comment notation supports interpolation, we can actually drop the coordinates, we can drop the coordinates into the output, into the string. Let's put some brackets around it as well. And then when we load that version into the browser, we'll see that each input intermediate matrix is now able to tell us which output element it corresponds to. So for example, if we had 2 intermediate matrices on display, we could see which was which. And then the last thing to show you is that when we have these 2 intermediate matrices here, we're actually able to interact with the intermediates as well, in which case we see both the downstream and the upstream dependencies. So this shows us that each intermediate matrix contributes to exactly 1 output element by averaging, but also that each element of each intermediate is coming from a kind of component-wise multiplication with an element from the filter and the input image. So we're still not all the way to a self-explanatory version of convolution, but it's still impartial information. We can't really see that it's multiplication, for example, that's establishing these data dependencies. But hopefully it's clear that this is quite a lot closer to an explorable explanation of convolution, and we had to do very little work to enable that. We just had to attach some dot comments into the computation. So that's where I'm going to stop. Thank you for your time. You can find out more about Fluid at our GitHub repository, and thank you very much again for listening.